Hi, I am Yildiz, a third-year PhD student at Northeastern University. So today I will talk about fast and accurate ranking regression, which is a joint work from Northeastern, Massachusetts General Hospital, and Oregon Health and Science Institute. Ranking observations are widespread in many domains, including recommender systems and medicine. For example, in a movie recommender system, the user may be provided with a couple of movies, and she can rank them with respect to her preference. Or in the medicine setting, a doctor may be provided with a couple of medical images, and she can rank them with respect to the severity of the disease that are in the medical images. So a common problem in this setting is to recover a total ordering of all of the samples in the dataset given these ranking observations, and also to be able to predict them in the future. So traditional learning from rankings is done via the Plackett-Luce probabilistic model. So in this setting, each sample is associated with a positive scalar score. And it's assumed that the probability of making a choice is proportional to the score of the chosen sample. So maximum likelihood estimation of these scores are traditionally done by parameterizing the resulting problem with the convex problem and solving the resulting problem via, for example, Newton's method. When you have large data sets, though, this may be prohibitively slow. So recently, my friend Grossgrasser proposed an efficient iterative algorithm to find the Plackett-Luce scores. So this algorithm relies on the fact that maximum likelihood estimation of Plackett-Luce scores are equivalent to stationary distribution of a Markov chain, where the transitions are defined by the ranking observation. And by doing so, they proposed an iterative spectral algorithm. These methods, though, are operating in the absence of features that are associated with the samples. But in many domains, for example, in the medicine, we have features associated with samples in the form of images. So the other variant that is doing ranking regression assumes that scores are parameterized functions of features. So traditional methods in this setting rely on classical optimization with respect to both shallow and deep parametric models. To the best of our knowledge, we are the first to do accelerated ranking regression via spectral methods. So our contribution starts with solving the ranking regression problem via alternating directions method of multipliers. By doing so, we decouple the learning of scores from the model parameters. And when we did that, we can still show that the scores are actually equivalent to the stationary distribution of a modified Markov chain compared to ALSR. And following this, we propose spectral algorithms that are akin to ALSR. Moreover, even though the problem that we solve is not convex, we can establish the guarantees that we have and the conditions that we have convergence for. And the algorithms that we propose, furthermore, give us gains in both speed and accuracy. Compared to ranking regression methods, we are up to 579 times faster in convergence. And also, when we have large data sets, we benefit from learning from features and outperform ILSR by up to 13% accuracy. So let's look at the technical formulation of it. So we assume that we have a data set of n samples where there is an underlying total ordering that we want to learn. And each sample is associated with p features that are denoted by x. And a labeler of this data set acts as a noisy oracle. So given that the subset of samples from the data set denoted by AL, she chooses the top sample that she prefers as CL. And L is the index of observations, and we have n such observations. And our aim is to reduce such choices CL from the features of the samples Xi that are in AL. So as we said before, Plackett-Luce model in this setting asserts that each sample is associated with a positive scalar score pi I, and the probability of making the choice CL out of AL is actually proportional to pi CL, normalized by the sum of the scores that are in the set of alternatives. And Plackett-Luce choice model immediately also expands to rankings where we want to rank rather than make a maximal choice. In this setting, ranking k samples is actually equivalent to choosing the first one out of all samples, then second one out of the remaining samples, and so on in an iterative manner. So keeping this in mind, right now we will focus on maximal choice setting. So maximum likelihood estimation in the set of ranking regression boils down to minimizing this negative log likelihood under the Plackett-Luce model. And we look into two parameterizations of the Plackett-Luce scores. First is the affine parameterization, where beta and B are the model parameters, and the other one is logistics. So due to time constraints, I will focus on only the affine setting. So also note that this problem is not convex because negative log likelihood phi is not convex. So if we go back to the setting of when we do not have features, as we said, Markov and Gross authors recently showed that maximum likelihood estimates of these scores are equivalent to stationary distribution of a Markov chain with the transition rates given by lambdas here. So if we show a graphical model that is equivalent, here nodes denote the sample and the transitions are governed by ranking observations. So what we show is a local minimum of the negative log likelihood is also equivalent to the solution of these set of global balance equations. So if lambda of the transition rates were fixed, we could easily find pi as a stationary distribution of the Markov chain by solving this linear system under a normalization condition. But here, lambdas are also functions of pi. So that is why my and Gross approach find pi's iteratively using the following iterates that they call AISTATS until convergence. So right now, when we expand this to ranking regression, we want to solve, as a reminder, this problem where we have the affine parameterization. So unlike the setting of ILSR, if we immediately write down the stationary points of the Lagrangian of this problem, we do not immediately get a set of Lorentz equations for a Markov chain. That is why we propose to use ADMM and decouple the optimization of scores from parameters. So this immediately brings the following speed advantage. So when pi and the dual variables of ADMM are given, the model parameters are a solution of a least squares problem with a closed form solution. And on the other hand, when beta and u are given, pi's can be found very efficiently using a spectral approach. And then, as in the standard ADMM algorithm, we update the dual variables. And we have this algorithm until convergence. So let's focus on the setting when we want to learn pi's at each ADMM iteration. So here, L rho denotes the augmented Lagrangian of the ADMM algorithm. And we see that the stationary points of the augmented Lagrangian are also satisfying the equation 15 on the right. So unlike the case of ILSR, where the right-hand side was 0, sigmas are in general not 0. But we can still show that in the following theorem. These actually are the global balance equations of a Markov chain with the modified transition range mu. That also depends on the sigma. Motivated by the observation that stationary scores at each ADMM iteration are also found by the stationary distribution of the Markov chain, we follow ILSR and find pi's at each ADMM iteration using the ILSR iterates that we call it ILSR with features. So overall, we propose Plackett-Luce ADMM algorithm, which is shortened as PL-ADMM, and we update pi, u, which are the dual variables, and beta iteratively until convergence using ADMM. And at each ADMM iteration, we use ILSRx until convergence to estimate the pi. So each iteration of ILSRx has the following computational complexity to first constitute the transition rates n, and also afterwards finding the stationary distribution using, for example, power method. And the updates of beta and u are very efficient in matrix multiplication since we can pre-compute the pseudo-inverse. We also show that even though the problem that we solve is not convex, for large enough rho, the stationary pi's that we find at each ADMM iterations are also a local optimum of the augmented Lagrangian. And moreover, for large enough rho again, PL-ADMM does converge to a point that satisfies the KKT conditions of the original constraint problem. So let's see the resulting algorithm PL-ADMM in action. So when we do predictions, we partition the dataset into train and test in two ways. First setting is sample seeding, where we partition the samples, in which case the training samples do not appear in the test ranking observation. So here PL-ADMM is the algorithm we just talked about, and PL-ADMM log is the case when we have logistic parameterization. And we also have some competing methods that we compare to. The first set of computing methods do not learn from features which are indicated by no X. So ILSR is the one that we talked about before, and denotes the minorizing maximization algorithm, which is state of the art for when we do not have features. And the other one is Newton and theta. This does, as we said before, the convexity parameterization of the problem and applies Newton's method to solve the resulting problem. And the other setting is doing ranking regression, as we said before. So Newton on data parameterizes scores with the logistic parameterization, as in PL-ADMM both, and solves the resulting unconstrained problem using Newton's method. And sequential least squares quadratic programming parameterizes scores with the affine parameterization and solves the same constraint problem that PL-ADMM solves. So in this setting, as we said, we have both speed and accuracy advantages. Compared to ranking regression methods, Newton on data as well as QP, our methods are 4 to 27 times faster in convergence time and still have very comparable accuracy. And on the other hand, since in this setting, train samples do not appear in test observations, the methods that do not use features, do not do ranking regression, are acting as random predictors. So by doing ranking regression and using features, we actually outperform the featureless methods, including ILSR, by 16 to 33% top-on accuracy and 16 to 30% Campbell-Tau correlation in prediction. The other setting that we have when we partition the data set is observation CV, where we partition the ranking observations, which leads to some training samples appearing in the test. So in this setting, actually, featureless methods do become relevant because they probably observe all the samples in the training, also in the test set. But here, when we, especially when we have more samples and to learn compared to the number of features P, feature methods are still very advantageous. By doing ranking regression based on P features compared to the domain of N samples, we outperform the featureless methods by 13% top-on accuracy and 9% KT, including ILSR. And as in the case for sample series, we still have a very good speed advantage compared to ranking regression methods, Newton on beta and SLS2P. So we have the similar observations on 3 different real data sets in our papers that are similar to synthetic data sets we've just seen. We also want to understand how the performance in terms of both time and accuracy relates when we change the number of samples, number of features, and number of observations. Here I will present the number of features dependency. We have the other observations in our paper. So as the number of features increases, our methods become more and more advantageous compared to the other ranking regression algorithm Newton on beta, up to 579 times when we have the largest amount of features. And also, compared to number of samples and when we have small number of features, the learning from features become advantageous in terms of predictions and resulting top-on accuracy compared to ILSR. And in this setting for 10 features, we actually outperform ILSR by 28% top-on accuracy. So in this paper, we propose a very efficient spectral algorithm to learn Plackett-Luce features as affine and logistic functions of sample features. Plackett-Luce scores. This can immediately be expanded to deep neural network models and would realize the following speed advantage. So as we see, if we have rankings compared to number of samples, the number of rankings in the dataset can scale exponentially compared to the number of samples in each query, which is query size. So if we have a deep neural network model and if we use our algorithm, at each iteration, we can learn scores efficiently using the spectral algorithm over this exponential ranking data. And after given these scores, we can actually do the regression of scores from the sample features, the linear approach compared to the case of exponential in the query side. Thank you for listening.